3 out of 4 AI coding assistants failed to fix the same bug correctly. Not partially failed. Fully failed. And one of them actually made the codebase worse. Today I am going to show you exactly what happened when I gave the same bug report to 4 leading AI coders, and why the results should change how you use these tools. AI coding assistants are everywhere right now. Developers are using them to write code, review pull requests, and yes, fix bugs. The pitch is simple: paste in your error, get back a working fix. But that pitch hides a dangerous assumption, which is that the fix is actually correct. I wanted to test that assumption properly. Not with a toy example, but with a real bug pulled from a real project. The kind of bug that has a non-obvious root cause and more than one plausible-looking wrong answer. Here is the bug report I used. A Node.js API endpoint was returning stale data to users even after a successful database write. The error logs showed no exceptions. The data in the database was correct. But the API response was consistently showing the previous value. I used this report, copied exactly, for every single test. I tested 4 tools, 2 standalone AI coding assistants and 2 ID-integrated tools that developers use every day. I am not going to name every tool in this narration because the point is not to shame a product. It is to show you a pattern. You will see the full names on screen throughout the video. AI coder number 1 responded fast. Within seconds it identified what it called a caching issue and suggested adding a cache control header to the response. The explanation was confident, well-formatted, and completely wrong. Cache headers affect the client, not the server-side data layer. The root cause was never touched. What made this answer dangerous is that it looked right to someone who was not deep in the codebase. The suggested code would compile, the tests would still pass, and the bug would still be there. This is the worst kind of wrong answer because it wastes time and builds false confidence. AI coder number 2 took a different approach. It asked me to paste the relevant function code, which I did. It then identified a potential race condition in the async flow and suggested wrapping the database call in an await block. This was closer to the problem space, but it assumed the developer had already made a common async mistake, which was not actually the case here. The third tool was the most confident of all 4. Its response was long, well-structured, and included 3 numbered steps with code blocks for each one. It diagnosed a read-after-write consistency problem in a distributed database setup. The only issue is that this project uses a single-instance database. The tool had essentially invented a more complex architecture and solved a problem that did not exist. This is a known failure mode for large language models. When they do not have enough context, they pattern match to the most common version of a problem they have seen in training data. A stale data bug in a distributed system is common. So that is what the model solved, regardless of what was actually described. Now for the tool that got it right. It started by asking a clarifying question: was the read operation happening on the same database connection as the write, or a different one? That question alone showed it was reasoning about the actual execution path rather than pattern matching to a category of bug. After I confirmed the setup, it identified the real problem. The ORM layer being used has a built-in identity map, sometimes called a first-level cache, that stores entity state per session. The write was committed, but the read was pulling from the in-memory session cache rather than hitting the database again. The fix was a single method call to clear the session before the read. The fix was 4 lines of code. The explanation was clear. And when I applied it to the original project, the stale data issue was gone. This is what a correct AI-assisted debugging response looks like. It traces the actual execution path, it explains the mechanism, and it produces a minimal targeted fix. So why did 3 tools fail? The biggest factor was context. The bug report I provided was accurate but brief. Tools that accepted the brief description at face value and jumped to a solution failed. The tool that asked for more information before answering succeeded. That is not a coincidence. Context window size matters here too. Tools with larger effective context windows can hold more of your codebase in mind while diagnosing a bug. But raw window size is less important than whether the tool actually uses that context intelligently. More tokens does not automatically mean better reasoning. The second factor is training data distribution. ORM session caching is a real but less commonly discussed bug pattern. The more commonly written about patterns, like race conditions and caching headers, dominated the responses of the tools that failed. This suggests those tools are better at common bugs than subtle framework-specific ones. Here is the practical takeaway. Before you apply any AI-generated bug fix, run it through 3 questions. First, does the fix address the root cause or just a symptom? Second, does the explanation match how the actual code in your project works? Third, could this fix introduce a new problem somewhere else in the code base? A useful habit is to ask the AI tool to explain its reasoning step by step before it gives you the fix. Tools that can walk through the execution path clearly are more likely to have actually reasoned about your specific problem. Tools that jump straight to code are more likely to be pattern matching. You should also test AI fixes in an isolated branch before merging. This sounds obvious, but a lot of developers, especially under time pressure, skip it. An AI answer that looks right is not the same as an AI answer that is right. The only way to know the difference is to test it. The bigger picture here is that AI coding tools are genuinely useful, but they are not equally useful for all types of problems. They are strong on syntax errors, common patterns, and boilerplate generation. They are weaker on bugs that require deep knowledge of a specific library, framework, or runtime behavior. Knowing that distinction will save you hours. Use AI tools for what they are good at. Be skeptical when the bug is subtle, the explanation sounds generic, or the tool skipped asking for more context before answering. If this comparison gave you a clearer picture of how AI coding tools actually perform under pressure, hit the like button. It helps other developers find this video. Subscribe for more honest, practical AI tool comparisons every week. Next up, I am testing whether AI tools can actually write secure authentication code from scratch, or whether they reproduce the same vulnerabilities every time. You do not want to miss that one.